So far in this series on sorting algorithms, we have talked about three of the sorting algorithms: selection sort, bubble sort, and insertion sort. And we have seen that these algorithms are not so fast. They are all big O of n square in average case. Now in this lesson we are going to talk about one algorithm which is big O of n log n in worst case. And this algorithm is merge sort. Big O of n log n time complexity in worst case is definitely a lot better, a lot faster than big O of n square in average case. So in this lesson we will study, discuss and analyze merge sort algorithm. There is one prerequisite for this lesson. You should have at least heard about recursion as a programming concept. Okay, so let's get started. Once again, I'll pick up a very simple sorting scenario. Given a list of integers in the form of an array, something like this. Let's name this array A. We have 8 elements in the array, so we have indices from 0 to 7. We want to sort this list in increasing order of the value of integers. So the list should be rearranged like this. Our approach in merge sort algorithm will be entirely different from what we had done in previous sorting algorithms, where we were rearranging the elements or changing their positions only by swapping or shifting. What we are going to do here is we are going to break this problem into sub-problems. We will divide this array into two equal halves, or rather two possibly equal halves. So we will find some middle position, and we can say that all the elements before this position belong to the first half and all the elements on or after this position belong to the second half. If an array would have odd number of elements, one of the halves will have one more element than the other half. We have 8 elements in the original array here, so we have two equal halves. Now think about this. What if we are somehow able to sort these two halves? And let's say these two halves are entirely different arrays. They are created separately in memory by copying values from the original array A. If we are somehow able to sort these two arrays, then we can merge these two lists together into the original list in sorted order. Of course, there has to be some algorithm to merge two sorted arrays into a third array in sorted order. The algorithm will be pretty straightforward. Let's say this particular subarray is named L and this particular subarray is named R, L for left and R for right. Because all the elements in A are present either in L or R, we can start overwriting A from left to right. We can start with 0th position in A. At any point, the smallest element will be either the smallest unpicked in L or the smallest unpicked in R. And let's say we color code the smallest unpicked in L and R by this yellow color. What we can do is we can pick the smaller of the two smallest unpickeds in L and R. We have two candidates here, 1 and 3. 1 is smaller, so we can write 1 here at 0th index, and now we can look for the number to fill at 1th index in A. Let's say the cells of the picked elements will be color coded in green. If I have to write pseudocode to merge the elements of two sorted arrays into a third array, let's say we want to write a function named merge that will take 3 arrays as argument, left, right, and the array in which it should be merging the two sorted arrays, left and right. Then I'll do something like this. I'll first take a variable that will store the number of elements in L and another variable that would store the number of elements in R. In a real program, we can also pass these two values to the function. Now I'll take 3 variables, I, j and k, and initialize them all to 0. Let's say I will mark the index of the smallest unpicked in L, j will mark the index of the smallest unpicked in R, and k will mark the index of the position that needs to be filled in A. For our example here, at this stage we have I equal 1, j equals 0 and k equal 1. Because we have already filled one element at index 0 in A, but when we will start with all 3 I, j and k as 0. And now my code will go like while I is less than NL. If NL is the number of elements in L, then for I to be a valid index, it should be less than NL. And similarly, for J to be valid, it should be less than NR. So while both these two indices are valid, both these indices I and J are valid, we can say something like if Li is less than or equal to Rj, so we are comparing the smallest in, or rather the smallest unpicked in L with the smallest unpicked in R. In this case, at kth position in A, we will write Li. Remember, we are overwriting A, and that's not a problem. And now I need to increment k, I need to go to the next position, and I also need to increment I to go to the next unpicked in L. And if this condition is not true, if Rj is less than Li, then Ak will be Rj. And once again we need to increment k, and we need to increment j to go to the next unpicked in R. This k equal k plus 1 is in both the conditions, if as well as else, so I have moved it out. Coming back to our example here, I and j are both valid indices. Now we'll compare if Li is less than or equal to Rj. Well, yes, Li is less than Rj, so we need to pick 2 for 1th index, and we need to increment both I as well as k, and for the next position it's between 4 and 3. 3 will go, and we will increment j and k this time. Next it's between 4 and 5. Next it's between 5 and 6. Next it's between 7 and 6. And after 6 has gone, we are done with all the elements in L. I is equal to 4 now, which is not a valid index. So in the while loop, this condition, while I less than number of elements in L, will be false. And this is definitely one probability. One of the arrays L or R will exhaust first. In that case, we need to pick all the elements from the other array and fill rest of the positions in A. After we come out of this while loop, we can write statements like while I is less than the number of elements in L. So we can check whether there are leftovers in L. We can do the same thing. We can say AK is Li, and then we can increment I as well as k. I'm short of space here, so I'm writing multiple statements in the same line. And similarly, we will write a while loop like while j is less than number of elements in R, we can fill in ak with rj, and this time j and k will be incremented. Once we are out of this first while loop, only one of these two while loops will execute, because only one of the sub lists or sub arrays will have leftovers. For this particular example, this third while loop will execute because the right sub array has leftovers, so we will fill up all the remaining positions. And finally we will have a sorted arrangement in A. This is our merge logic, and there are a couple of ways in which we can clean up this code further, but for now let's just understand the logic. And now coming back to where we had started. In the beginning we had imagined that if somehow these two subarrays or sublists, I'm redrawing the unsorted original array and the unsorted sublists. So we had said that if we are somehow able to sort these two lists, then we can merge them back into the original list. But of course we need to have a deterministic logic to sort these two sublists or subarrays also. And the logic is we can break these sublists even further. So this sublist comprising of 4 elements 2, 4, 1 and 6 can be further divided into these two halves, and this list comprising of 8, 5, 3, 7 can be divided into these two sublists 8, 5 and 3, 7. The solution for 2, 4, 1, 6, this particular sublist, can be constructed after we sort these two sublists 2, 4 and 1, 6 and merge them back. And similarly we can sort these two lists, sublists, and merge them back to sort this 8, 5, 3, 7 sublist. Once again we have these 4 sublists of 2 elements each, and they can also be divided. What we are basically doing here is that we are reducing a problem into sub-problems in a recursive or self-similar manner, and at any step, once we get solution for the sub-problems, we can construct the solution for the actual problem. If we have 2 sorted sublists, we can sort the parent list also. We can go on reducing a sublist only till we have more than one element in the sublist. Once we reach a stage where we have only one element in a sublist, then we cannot reduce that sublist any further. So once we reach a state where our sublist has only one element, our recursion will end. And a list with only one element is always sorted. We do not need to do anything to sort it. Now at this stage we can start combining back or merging the sublists. So these 2 sublists can be merged. Let's say we will depict the cells in sorted sublists in green. We have already discussed the merge logic. This sublist 2, 4 will still be the same after merge also. Sublists 1 and 6, these 2 sublists with only one element each will also merge, and now we can merge 2, 4 and 1, 6. Coming to this side, all these sublists with just one element are already sorted, so we will start merging back. Finally these 2 sorted sublists 1, 2, 4, 6 and 3, 5, 7, 8 can be merged back into the original list A. And now let's write pseudocode for this algorithm. I will write a function named merge sort that will take an array A as argument. In the function, first I'll take a variable that will store the number of elements in A, and now we can partition A into 2 halves. We need to partition A only if n is greater than 1. If n is less than 2, then we have only one element in the array, so the array is already sorted. We can simply return. Else what we can do is we can first find out a middle position, and then we can create 2 arrays, one of size equal to mid and another of size n minus mid. So first array will have all the elements starting index 0 till n mid minus 1. We can just fill the elements. We can run a loop from 0 to mid minus 1, so there will be mid elements in all, and we can say left I is AI, and then we can run another loop from index mid till n minus 1, so there will be n minus mid elements in all, and we need to fill in right I minus mid as AI. Now that we have created left and right sublists, we can first make a recursive call to sort the left sublist, and once we are done sorting the left sublist, we can make a recursive call to sort the right sublist. And once both left and right sublists are sorted, we can make a call to the merge function that we had written before to merge left and right sublists into A. It's really important to visualize how this recursion will actually execute. Once again, I'll start over with an unsorted array, and let's say this array is passed to the merge sort function. Now let's run through this code and see what's happening. I'll start with the first line. We calculate n, the number of elements in the array. The number of elements in this array is 8. It's not less than 2. This condition is not true, so we will not return and exit from this function. We will move forward. We will calculate the mid index. Now n is 8, so mid will be 4, and now we will create 2 arrays, left and right, one of size mid and another of size n minus mid. We will fill up these arrays. The first 4 elements will go to left and next 4 will go to right, and now we are making a recursive call. When a function calls itself, then such a call is called recursive call. A function calling itself is not much different from a function A calling another function B. At this stage, the execution of this particular function call with this array with 8 elements as argument is paused, and the machine says that, hey, let me go and finish this particular function call and then I'll come back to you. The machine goes on to execute merge sort on this particular array with 4 elements 2, 4, 1 and 6. Now once again we start at the first line in a new call to merge sort for this new array. N is not less than 2, so we will not return and exit. This particular condition is the base condition or the exit condition from the recursion. If this was not there, we would have gone endlessly in recursion. We needed to stop somewhere. Once again we will create lefts and rights, and once again there will be a recursive call passing this array 2, 4 as argument. So once again the state of execution of this second merge sort will also be paused. All of these are paused. The state of execution of these functions, the function calls with these arrays as arguments, are paused. This one is executing. Now once again here also we will have a recursive call. Now for this particular array with just one element, this base condition will be true. So this call will simply exit. And now for this guy, this array with 2 elements 2 and 4, this second recursive call will be made with just this element 4, which once again is the base condition. And now once both the merge sort, both the recursive calls for this particular sublist with 2 elements return back, merge function will be called, and then this guy will finish, and then the control will return back for execution of this particular sublist 2, 4, 1, 6, and this guy will make the second merge sort call. This guy will first make a call for this sublist with just one element, and once this is done it will make another recursive call. Now we will have a merge for this guy 1, 6, and then control will return back here to this array 2, 4, 1, 6, and merge will be called for this guy. And now once this guy 1, 2, 4, 6 will finish, the control will return back to the function call corresponding to the original array, and this guy will make another recursive call, the second merge sort call. In actual implementation we must make sure that all these extra spaces and extra sublists that we are creating should be deleted from the memory once we are done using them. Like at this stage we do not need all these arrays with 1 and 2 elements in the memory. Now for this guy 8537 we will have a recursive call passing 85, that will again make a recursive call with just one element 8, and then we will also have a call to 5 that will simply return. Once 5, 8 returns, we will have call for 3, 7. 3 and 7 will simply merge, and now 5, 8 and 3, 7 will merge. And finally when execution for 3, 5, 7, 8 will finish, we will have a call to merge for the original array or the initial array. So this is merge sort algorithm for you. At the start of the lesson we had said that this is big O of n log n in terms of time complexity. In our next lesson we will implement this algorithm, we will run some real code, and we will also analyze the time and space complexity of this algorithm. This is it for this lesson. Thanks for watching.